Hello. So today the webinar will be held by David Vaccaro. We're just waiting for him to join. Ah, something. Okay. Okay. David is going to be here in 1 minute. Yes, it's math today. It's matrices. Today we're going to talk about matrices. Yes, that is the next assignment. Matrices and mappings, or more importantly, mappings. Sort of operations on vectors. Apologies for the delay. I'll double check that everything's fine. If you have a question, you can ask me. If you have a question, oh, here's David. Hello, David.
Sorry about that. Just getting back from London, working, just doing something very similar to school at a school there. So, been doing lots of maths and physics today, and we're doing matrices and transformations. Is that right?
Yes, and the assignment hasn't been published yet. So
okay.
Yes.
Excellent. Well, that's fine. We can look at some of the questions, and actually, I think that works quite well because it's quite a meaty assignment. So, this is the matrices and mapping sheet. Can people see my screen?
Not yet.
Not yet. There was an awful moment on Tuesday when I was in full flow, using generating functions to get a formula for the Fibonacci numbers, and then someone piped up and said, "Oh, your screen had stopped sharing." So there was a long section of me describing making partial fractions of various functions, and they couldn't see me. Right. So let me make sure I actually share my screen. Right. Can people see it now?
Yeah, it's visible.
Excellent. So the first thing we're going to introduce is a wonderful thing, which is the space Rn. Now, I think we're all, from quite a young age, used to the plane. So we've got our x and y axes, and we can represent a point in the plane as a pair xy. And then when we're a little bit older, we move into 3 dimensions. And we can represent a point in 3 dimensions as a triplet x, y, z. Or alternatively, we can think of a point as having a position vector, which is the column vector x, y, or in 3 dimensions is the column vector x, y, z. One of the things which surprised me when I went to university, and the first time I saw it, I was completely blown away by it, is that once you get to university, lecturers do everything in Rn, so n dimensions. And at first glance, this just seems bizarre because you don't have a mental picture anymore of n dimensions. And I'm going to steal my supervisors from Cambridge's example, though. So what he's pointed out was that a dimension is a degree of freedom. And there's one place. So if you want to understand Rn and something with n degrees of freedom, what he said you should do is you should go and work And I hope it's okay to do product placement, but he said you should go and work in McDonald's. Now, what did he mean by this? So if you imagine an order in McDonald's, you could order a certain number of Big Macs, a certain number of fries, a certain number of chicken nuggets, and I'll just do it in 4 dimensions, and then a certain number of Cokes. So an order in McDonald's has 4 degrees of freedom, so you could represent it by a 4 vector. Now, for the physicists amongst you, will meet a very famous 4 vector, which is the 4 vectors that you meet in relativity, where you've got the 3 spatial dimensions and time. But let's stick in this sort of Big Mac world at the moment. So we could imagine ordering 5 Big Macs, 4 portions of fries, 6 chicken nuggets and a Coke, and we could represent it as a vector like this: 5, 4, 6, 1. Now, what also we can do once we've got vectors in Rn is we could imagine some sort of transformation. And can anyone think of a very natural transformation in the context of McDonald's, which would map this 4 vector onto, let's just do a single real number R. So what would if you ordered 5 Big Macs, 4 portions of fries, 6 chicken nuggets and a Coke, what might the person behind the till then do to that order? What sort of transformation, what sort of mapping might they do to that onto a number? So into the chat. Oh, nothing yet in the chat. Dot product are excellent. Okay. So someone said dot product with prices. And it's very good that you recognize that as a dot product. So I don't know the prices in McDonald's. I haven't been for a long time, but let's imagine that a Big Mac, and apologies if my prices are completely wrong, but let's say a Big Mac cost £3, fries cost £2, chicken nuggets cost 50p, and a Coke cost £1. Then a natural transformation would be the mapping 5, 4, 6, 1 maps to 3 times 5 plus 2 times 4 plus 0.5 times 6 plus 1 times 1. And all I've done there is I've taken the components of the prices, so the 3, the 2, the 50p and the 1, and I've combined them with the components of the order, the 5, 4, 6, 1. Okay, someone else mentioned you could also just do a mapping to decide how many things you've bought. So if you've bought 5 Big Macs, 4 fries, chicken nuggets and a Coke, you've bought a total of 16 objects. Now, the normal way of representing this linear transformation is to represent the components which represent the mapping as a row vector. So 3, 2, 0.5, 1. And then I'll do the mapping, which is just summing the components as 1, 1, 1, 1. And then to do this matrix multiplication, which is multiplying along the row and down the column. So that would take us to, we said 16 objects, and 15 plus 8 is 23, plus 3 is 26, plus 1 is 27. So that's 27. So what we've mapped is we've mapped here the 4 vector, which is Big Mac, fries, chicken nuggets, and Cokes. And we've mapped it to the 2 vector, which is the price and the number of objects. And this transformation is a linear so this would be a linear transformation from R4 to R2. And we say that this object, so this object which includes the numbers that we sort of, inverted commas, dot product with, we call this, the green object, is the matrix of the transformation. Okay, so let's, I feel bad, I'm going to spoil the sheet a little bit for you. But let's have a look at the first problem from the sheet. So it says, in a football championships, 3 points are awarded for a win, 1 point is awarded for a draw, and no points are awarded for a loss. It then says, let R1 equal W1, D1, L1 represent the results of a football team in the first half of a season. So this is a vector, which is why it's bold. And R2 represent the results in the second half of the season. So my first question is going to be, how many games? So find the matrix T that computes the number of games played and the total number of points. Okay, so let's do it in the first half of the season. So W1, D1, L1, and we're going to map to played and points. So in the chat, or if you're watching this on catch up, pause the video and think, what is the matrix of this transformation? So what will we do in the top row? What do we do to W1, D1, and L1 to convert to the number of games played? And what do we do to W1, D1, and L1 to convert to the number of points? Well, hopefully you'll agree that the number of games played is just W1 plus D1 plus L1. And in matrix speak, that would be multiplying by the matrix 1, 1, 1. So that row vector. And to convert to the number of points, because we get 3 points for a win, 1 point for a draw, and 0 points for a loss, the conversion numbers would be 3, then 1, then 0. And so if we want the overall matrix would just have rows 1, 1, 1, 3, 1, 0, W1, D1, L1, which maps to W1 plus D1 plus L1 and maps to 3W1 plus D1, which is the number of games played and the number of points. Okay. The notation might be the notation might be unfamiliar. So I'll just give people a little bit of a chance to stare at it. And if you're happy and ready for me to continue, just put a thumbs up in the chat. Excellent. It's I don't know the history of it, but I always find it a little bit unfortunate that pure mathematics and Excel does things the other way around. So in Excel, when I've got my Excel brain on, I would consider a vector of information to normally be a row, whereas in pure mathematics, a vector of information is normally a column. But I think it's too late to sort that out. Okay, so what have we done so far? We've stated the matrix of the transformation. So this is the mapping which takes us from the won, draw and lost vectors to the played and points vectors. Okay, part B on the sheet says verify and explain the relationship TR1 plus TR2 is equal to TR1 plus TR2. So I'll do the verify bit first. And while I'm doing the verify bit, maybe try and do the explain bit yourself by putting an explanation into the chat. So the verify bit is to look at what happens if we apply the transformation T to the sum of the two results vectors, so the W1, D1, L1 plus W2, D2, L2, which is just applying T to W1 plus W2, D1 plus D2, and then L1 plus L2. And that converts the results matrix into the played matrix, which is W1 plus W2 plus D1 plus D2 plus L1 plus L2. And then we've got 3 times W1 times W2 for the points for the wins. Then we've got 1 plus D1 plus D2, nothing for the losses. And if we just re-bracket everything, so if we just use commutativity of addition, we can put all the ones together. All the twos together. Then split the vector into 2 parts. And then recognize that these 2 vectors are just the matrix T applied to the first half of the season plus the matrix T applied to the second half of the season, which is what we wanted to show. Okay, so this is the verification. And now I'm going to have a look at the chat and see if anyone's explained it, or if anyone's feeling super brave, they can unmute themselves and explain it. So can anyone explain that result? So I've done a sort of calculation that verifies it, but can anyone explain why this is actually a really familiar observation? So what does TR1 plus R2 represent? This represents the number of games played and the number of points over the whole season. Okay, now what I think is intuitively obvious is that you can do this in two different ways. One way would just be to calculate the whole result, so to add R1 and R2 and then convert to played and points, or you could just add the number of games played in the first part of the season to the number of games played in the second part of the season, and the number of points in the first part of the season and the number of points in the second part of the season. Okay, so it doesn't matter if you add results and then convert, or if you convert and then you add. Okay, and this this relationship is essentially one part of the categorization of the map, what we mean when we say that the map T is linear. The other property of a linear map is that if you look at T applied to a multiple of a vector, that's the same as multiplying the image by lambda. These two conditions together, 1 and 2, say that T is linear, and they can serve as a definition for linearity. And that's one of the other problems on the sheet. Okay, any questions? Any questions about that? If you're happy with that, put a thumbs up in the chat. If you've got any questions, put them in now. Otherwise, we'll move on to another question. Excellent. Good, good, good. I'm sorry, I'm just going to the sheet. Let's have a look at, this is a very nice problem. This is very physicsy. So what we're going to have a look at here is complex numbers. So what we're going to look at here is relating something which is familiar, which is multiplication by complex numbers. And we're just going to find an alternative way of representing it. And the alternative way we're going to represent multiplication by complex numbers is as a matrix. So the first thing I'm going to do is I'm just going to fix a complex number, which I'm going to call W. So it says, the question says, let W equal A plus IB. Actually, I'll let you decide whether it's a W or a omega. And I'm going to take a complex number Z, which is X plus IY. And I'm going to look at the effect. I'm going to look at what we get if we multiply W and Z together. Okay, so WZ is A plus IB times X plus IY. And if I open the brackets, I get AX plus AYI plus BXI. And then I get an I squared term, which is minus BY. So I get AX minus BY plus AY plus BX. Okay, and this is in the complex world. So what I've got here is a mapping F, and I'll call it FW, which maps C to C, and which just takes a complex number Z and spits out WZ. But what I can also do, if I wanted to, is I could think of a complex number, X plus IY, as a vector in R2, which is the vector XY. So I'm just going to consider some natural mapping, and it's called the infix mapping. So I'm going to represent it by the Greek letter iota, and iota Z is going to be XY. Now, what is iota? So what is the mapping of FWZ? Well, I found that it was the complex number AX minus BY in the real part, and AY plus BX in the imaginary part. So in the world of R2, so if I think of this sort of mapping FW as a mapping from R2 to R2, then XY maps to AX minus BY and AY plus BX. Actually, I'll write it as BX plus AY. We'll see why in a moment. Unless I'm just going to check if everyone's awake and watching. What would be the matrix of this transformation that I've just written down? Excellent. One person's awake. Well done. Okay, so if we look at the first row, the components of X and Y are A and negative B respectively. And if we look at the second row, the components of X and Y are B and A respectively. So XY maps to this matrix transformation. So in some sense, multiplication by W in the complex plane does the same thing as multiplication by this matrix in the when we think of complex multiplication as a mapping from R2 to R2. So in some sense, this matrix A minus B, B, A represents the complex number W. And I'll just try and convince you of this relationship in another way. So can anyone think of a different way of, if I take this matrix A minus B, B, A, can anyone suggest in the chat, or if they're very brave, unmute themselves, can anyone think of a different way of representing this matrix? Can anyone think of a way of decomposing it maybe into two matrices? Okay, well, I've got some of my terms involve an A, and some of my terms involve a B. So I could write this matrix A minus B, BA as A times 1, 0, 0, 1 plus B times 0, negative 1, 1, 0. Now, some of you might have studied matrices before. Can anyone suggest what this matrix is? So what does this matrix do? Excellent. Someone's put in the chat, it's the identity it maps to itself. Let's see what this means. So if we consider the matrix 1, 0, 0, 1, and we look at its action on xy, then the output is xy. So this matrix 1, 0, 0, 1 is what is called the identity matrix. Right, this one might need a little bit of a deeper knowledge of matrices, and it might be hard to spot if you've not studied it before. But let's try and figure out what this matrix does. 0, negative 1, 1, 0. So 0, negative 1, 1, 0 maps xy. So let's do our matrix multiplication. So we get negative y x as the image matrix. Now, I'd be very impressed if anyone can spot this having not studied matrices before, but can anyone suggest what this second transformation does? Ah, well done. We've got a suggestion in the chat for rotation 90 degrees anti-clockwise. Okay, let's see if this is correct. So let's consider the mapping which takes the vector x across and y up, so x, y. And maps it to negative y in the x direction. I shouldn't have drawn my y and x so similar. I'll make the y smaller. And then an x in the up direction. So this is rotation 90 degrees anti-clockwise. So I'll just get rid of this now. So we've now got this matrix A negative B, B A is A times the matrix, which is the identity, plus B times the matrix, which is rotation by 90 degrees anti-clockwise. Now, remember that this matrix, A minus B, B A, is the matrix which did to vectors in R2 the same thing as multiplication in complex numbers by this complex number A plus IB. Now, has the scales fallen from people's eyes in any way? So what I mean by that is, can anyone see why is this complex number, can anyone explain the relationship between this complex number A plus IB and this matrix in light of this decomposition? Maybe that's a little bit of a Zen question. Well, okay, let's think of it this way. Which complex number can we think of? Which complex number can we think of as being this first identity matrix, 1, 0, 0, 1? Well, if my complex number was 1, then the matrix of the transformation would just be 1 times 1, 0, 0, 1. So we can think of this identity matrix is in some sense the same as multiplication by 1. Which complex number would give me this second matrix, this negative 1, 1, 0? Well, I would just want there to be a component of B. So if my complex number was I, then the matrix would be 0, negative 1, 1, 0. So this matrix, which is my rotation by 90 degrees, is the same as multiplication by I. By the complex number, little I. Now let's see what this makes sense. So I'm just going to call this matrix negative 1, 1, 0. And I think everything will fall into place when I square it. So grab a little sheet of paper or make a mental guess of what I'm going to get. But what do you think is going to happen if I square the matrix 0, negative 1, 1, 0? Excellent. I think someone's put what it is in the chat and they've got the big picture. Okay, so let's multiply out the matrix. So this row and this row gives me negative 1. The second place is 0. This place is 0. And this bottom corner is negative 1. That's negative the identity matrix. But the identity matrix is the matrix that we're thinking of as being like the number 1. So this matrix, 0, negative 1, 1, 0, is the square root of negative the identity matrix. So this matrix is the square root of negative 1. Okay, and so that now makes sense of this decomposition, that a complex number is like A times the identity matrix. So that's like being A times 1 plus B times this matrix here, 0, negative 1, 1, 0, which is the square root of negative 1. And then geometrically, we know that the multiplication by the complex number I is rotation by 90 degrees anti-clockwise. Okay, so what that means is that, and this isn't what happened historically, but historically, we never needed to introduce complex numbers. Okay, we could have regarded this set of matrices okay, so this is in the set of matrices 2 by 2. Okay, we could have defined, I'll just put A, B, and R. We could have defined this set of matrices as being the complex numbers. Okay, a little good word for you. Okay, and I'm interested to know if anybody knows the word. Does anybody know the word? And it's a word you'll meet when you do maths at university, that expresses the idea that the set of complex numbers on the one hand, so A plus IB, and this family of matrices on the other hand, A, negative B, BA, are in some sense the same, that they have the same algebra. Does anyone know the adjective that describes that notion of sameness? If not, then you're going to learn a new word for the day. Okay, the word of the day is isomorphism. So we say that they're isomorphic. So it basically means they've got the same algebra. A good example of like natural sets that are isomorphic are like the natural numbers 1, 2, 3, 4, 5, and the Roman numerals I. They've got the same. You know, you can just map one to the other and they've got the same algebraic properties. So this matrix family and the complex numbers have got the same algebraic properties. It's a little window into higher level maths there. But does anyone have any questions about that question, or are we happy to go on? No comments? People still there? Happy to go on. Excellent. Okay, good. Right, let's go back to the sheet. So my screen is. So the next part of the sheet looks at something which we've already sort of looked at to a certain extent. It's looked at linear transformations of the plane. So it turns out that certain transformations can be represented by matrices. And I'm going to give a really important example, and I'll just find the example here. So this is an example from the problem sheet. This is good that this is an example. And this is going to give me an example of a very important transformation that is can be represented by a matrix. Let's read it. So the following diagram shows a triangle, 0, 0, x, 0, and xy. So that's this pink triangle. And it's rotated by theta degrees so that this point xy maps onto this new point up here. And what we're going to try and do is we're going to try and get the coordinates of what the example asks me to do is to find the coordinates of the new point and then to show that rotation by theta can be represented by a matrix. So this is just a nice bit of geometry to try and find the coordinates of the image P'. So first of all, this length here, OA, is x. So this length along here is x. So by simple trigonometry, can anyone suggest in the chat the length ON? Excellent. People have just recognized that as a cosine, so we're essentially resolving forces. So this horizontal distance is x cos theta. And then this vertical distance, NA, is x sine theta. We can do a little bit more geometry. We can say that this distance here from A' to P' is y. We can do a little bit of angle chasing and say that this angle is 90 subtract theta. We can also say that this angle in here is 90 subtract theta. This angle in here is 90 subtract theta. So this angle up here is theta. We can now do a similar resolving. So this vertical distance here, so this distance RS, is just y cos theta. And this horizontal distance here is y sine theta. So I can now find the coordinates of x dash y dash. So x dash y dash, the x coordinate is, I'll write it as a column vector. So x dash y dash. The x coordinate is ON, which is x cos theta. And then we subtract MN, which is y sine theta. And then in contrast, y dash is x sine theta plus RS, which is plus y cos theta. And so as a matrix, this is cos theta minus sine theta, cos theta. Okay, now I'm going to give a real bonus mark for anyone in the chat who recognizes, can anyone tell me what type of matrix this is and why? So this is my rotation by theta matrix. What form does this matrix have that we've seen before, and why? Now I've got an that's cool in the chat, but I think there's something even cooler in the, yes, someone's put it in the chat. I'm so happy. They've said that this is the matrix of a complex number, because this this matrix has got this format that we saw earlier of being A negative B, B, A. It's called antisymmetric. But this is the matrix of the complex number cos theta plus I sine theta, which we know is the complex number e to the I theta. And we know that multiplication by e to the I theta is a rotation by theta. Okay, and in the words of whoever that was in the chat, I think that that is pretty cool. If that's not cool, I don't really know what maths is cool. Okay, let's go back to the example on the sheet and look at what it asks me to do next. So it says, show that the transformation r theta that represents a rotation by theta is linear and find its matrix, which we've just done. And now it says, prove that r phi times r theta is r theta plus phi. Okay, so let's do C. So C asks me to prove r theta times r phi is equal to r theta plus phi. So let's do this. So we've got cos theta sine theta minus sine theta cos theta, that's r theta. R phi is just going to be the same things with phi's in. And let's see what we get. So we do our matrix multiplication. So we do cos theta minus I sine theta, and we multiply by this column. So we get cos theta cos phi minus sine theta sine phi. Then we do the next multiplication, and we get minus cos theta sine phi minus sine theta cos phi. Then down here we get sine theta cos phi plus cos theta sine phi. And then finally we get cos theta cos phi minus sine theta sine phi. But let's look at each of the 4 bits. Cos theta cos phi minus sine theta sine phi, well, that's just a compound angle formula. That's just cos theta plus phi. Sine theta cos phi plus cos theta sine phi, well, that's just a compound angle formula. So that's sine theta plus phi. And then the other terms are the same, but with a different sign, or exactly the same. But what do we have? We now have just our rotation matrix, but we have r theta plus phi. Can anyone give me a much more simple explanation for this matrix identity. Why did it have to turn out to be the case that r theta times r phi is r theta plus r phi? Why is that in inverted commas obvious? Excellent. Okay, because what we've done is we've done two rotations. We've done a rotation by theta and then a rotation by phi. But if you rotate by theta and then by phi, you've done a rotation by theta plus phi. So actually, there's two ways that we could have looked at this calculation. On the one hand, we could have looked at it the way that I've just done, where I've assumed the compound angle formulas and proved this result about matrices, that r theta r phi is r theta plus phi. Or we could have taken this as a geometric fact, and that then gives a proof of the compound angle formulas. Okay, this relationship must be true geometrically. And so this matrix, which is the r theta plus phi matrix, must be the same as this matrix. And the only way that that can be true is if the compound angle formulas hold. So this example on the sheet, we can regard as a proof of the compound angle formulas. Okay, I'm just going to pause there. Does anyone have any questions about that example? No questions. Does anyone agree with me that that's kind of cool? There's a yes. There's another yes. I think you're just right. Okay, let's look at something equally cool. Okay, and this turns out to be a very important idea in transformations. Does anyone here do the Rubik's Cube? I'm surprised. No, there's no yeses. Normally, if you take a bunch of mathematicians, lots of people who do maths do the Rubik's Cube. But people who do the Rubik's Cube, try and think where this idea that I'm about to show you, where you use it when you solve the Rubik's Cube, or how you use it in certain tricks that you do when you solve the Rubik's Cube. So I don't think this is actually on the sheet, or maybe it is. Let me check. I think I might have cut it off. So I've just done. No, okay, this is not on the sheet. Okay, but something similar is. Okay, fine. Right. So this is kind of the example on the sheet, but we're going to do something slightly different. Okay, so example 4 says identify the transformations T and R theta. So let's start with the transformation T. So the transformation T has got matrix 1, 0, 0, negative 1. So let's see where this takes the point xy. So this maps xy to x, negative y. So can anybody put in the chat a suggestion for what the matrix T does, what transformation is affected by T? Reflection in the x-axis is a suggestion. Let's see. Well, it takes the point x, y, and it flips the sign of the y component to x, negative y. We should really do it with column vectors, so it takes x, y to x, negative y. So this is reflection. So T is reflection in the x-axis. And r theta we've just met before. This is rotation by theta about the origin. Okay, so my question is, find the matrix of reflection in the line inclined at theta to the x-axis. So here's the angle theta. And what I want is I want the matrix that represents reflection in that line. And I'll just do a little snip. And I'll color this line actually, before I do the snip, I'm just going to, this oblique line, I'm just going to color it in a different color. I'm going to color it blue. And now I'm going to do the snip. So we know the matrix of T and we know the matrix of R theta. Can anyone think how to find the matrix of reflection in this line theta? Can anyone think of a strategy? Oh, we've got a Rubik's Cube. We've got a Rubik's Cube person. Very important idea here. So we know how to, we've got this line and we've got this x-axis. And we know how to reflect in the x-axis, but we don't know how to reflect in our line. So can anyone suggest what we could do to turn our line into the x-axis? So what transformation could we do to map this line onto the x-axis? Well, we just could rotate by negative theta. So I'm going to do the rotation by negative theta. And so that's going to take the point A to the point B. And it's taken the blue line to the x-axis. What can we do next? Overall, we want the matrix, which is the reflection in the blue line. But what we can do next, excellent, someone's put it in the chat. They've said we can reflect and then rotate back. So what we can do, now that we've got the blue line is now the x-axis. So this is the normal world over here. This is the transformed world, where the blue line is equal to the x-axis. And then what we can do is the matrix T, and that will take B to C. Okay, because we've just reflected B. And the blue line is the x-axis. And then what we can do is then we can turn everything back to normal. And we can take the blue line back to where it was before by rotating by theta. So here we've got C has now mapped onto A dash. Okay, there's an obvious elephant trap. But my reflection in the blue line, I'll say it's got matrix M. Let's see who's awake at 7:15. Can anyone tell me what the matrix is for M in terms of R negative theta, T, and R theta? So what we've done is we've got our line, we've reflected, so it's the axis, we've reflected, and then we've rotated back. So we've done an inverse rotation, a reflection, and then a rotation. Oh, I can't read the... So what I'm trying to get people to put in the chat is what this transformation is, and there's an elephant trap that is natural to fall into. Okay, we've got three transformations: R negative theta, T, R theta. But if you think back to GCSE, the order of composition is from right to left. So the matrix M is, we read it in this direction. It's R theta, T, R negative theta. So let's see what we get. So R theta, we remember, is cos theta minus sine theta. Sine theta, cos theta. T is 1, 0, 0, negative 1. And R negative theta is cos theta sine theta, 0, negative cos theta. Sorry, what am I doing? Not 0. Negative sine theta, cos theta. Don't know what I was doing at all then. I think I was starting to matrix multiply. So this is my R theta, this is my T, this is my R negative theta. So now let's open the matrices. Now we get cos theta sine theta. Then we get sine theta minus cos theta. And then we multiply, so then we get cos squared theta minus sine squared theta. Then we get 2 cos theta sine theta. Then we get 2 cos theta sine theta. Then we get sine squared theta minus cos squared theta. So we get minus cos squared theta minus sine squared theta. Let's see if we recognize any of the terms. So this is cos squared theta minus sine squared theta. So cos squared theta minus sine squared theta is cos 2 theta. 2 cos theta sine theta is sine 2 theta. 2 cos theta sine theta is sine 2 theta. And then in the bottom, we've got negative cos 2 theta. Let me just... Oh. So this matrix M is reflection in the line, reflection in the line theta. Okay, any questions? Oh, the question. Oh, someone's phone powered off. Could I go over this again? Okay. So the question was this. I don't mind going over this because this is a really important example, or kind of an example that one will meet similar things again. So we started with a matrix which was reflection in the x-axis, and a matrix which was rotation by theta about the origin. And the question asked me to find the matrix of a reflection in the line that was inclined at an angle theta. So this blue line here. So can I find the matrix that takes this point and then reflects it to the other side of the line? And the really clever idea that I had was to take my line and map it onto the x-axis by rotating by negative theta. So the point A becomes the point B. But I then know how to reflect in the x-axis because I can do the matrix T. So the point B goes to the point C. And then I can just rotate back, so the line is the line again. So overall, my matrix is R theta T R negative theta. Okay, and this idea is called conjugation. And then what I did is I then just multiplied the matrices together, and I found that the matrix M was cos 2 theta sine 2 theta sine 2 theta minus cos 2 theta. Okay, interestingly, and I won't necessarily show how I found this, that is the same as this matrix, which is T, and this matrix, which is R 2 theta. So what geometric fact have I just proved about reflection in this line? Well, reflection in the line in this line L is the same as rotating by 2 theta and then reflecting in the x-axis. So a rotation and then a reflection is a reflection. Does that answer your question? Who was it? Yeah, it's not. So the person in the chat said, oh, it's equivalent to a rotation by 2 theta. This matrix here, M, is very similar to, but not quite the same as a rotation by 2 theta because the minus is in a different place. Okay, so what? But what is the case? Is no. So this matrix M is a rotation by 2 theta followed by a reflection. Actually, no, I think it's the other way around. Let me think. Oh, it's a rotation by negative 2 theta followed by a reflection, which is actually the same as R2 theta t. Okay, what we've veered into there is matrices have started to tell me how reflections and rotations multiply with one another. I'll just finish with a little bit of homework, but this will take you into another bit of maths that you will see a lot in future work. So this is homework because I'm not going to be able to do it all in 5 minutes. Okay, I'm going to draw a square whose center is the origin. Okay, so this point is 1, 1. This point is negative 1, 1. This point is negative 1, negative 1. This point is 1, negative 1. So question, and put your answers in the chat, is what symmetries of this square exist? So what are the symmetries of a square centered on the origin? Or if you don't want to put too much in the chat, just tell me how many symmetries there are. Okay, well, you should notice that there are 8 symmetries. There's rotation by 0 degrees, rotation by 90 degrees, rotation by 180 degrees, rotation by 270 degrees, and then there's 4 reflections. Okay, so I can call this reflection T1, this reflection corner to corner T2, this reflection T3, and this reflection T4. Okay, and the exercise I've got for you is to if you want, and this will give you a lot of practice because you'll end up doing 64 matrix multiplications, although some of them would be easy because you know what the answer is going to be. But let's just see what happens when you compose them. So let's do R90 first and T1 second. So T1 is reflection in the y-axis. So the matrix is -1, 0, 0, 1. R90 is rotation by 90 degrees anti-clockwise. So it's 0, 1, -1, 0. This is R90. Let's see what matrix we get. So -1 times 0 is 0. -1 times -1 is 1. 0, 0, 0, 1. 0, 0, 0. So we get this matrix. But this is the matrix which takes x, y to y, x. But that is just reflection in the line y equals x. So that's reflection in this line. So we get T2 here. Okay, and so a little bit of an exercise is if you fill in this grid will give you a multiplication table for the symmetries of the square. And I'll finish with a general knowledge question before I just take any general questions from you guys. Does anybody know what the name is for the multiplication table of symmetries of an object? So this table, if we were to complete this table, what's the name of the mathematical structure we would get? No word is coming into the chat, so you're going to learn a second new mathematical word of the day. Okay. The word for the way in which the symmetries of a shape multiply together is one of the overarching sort of like fundamental concepts in mathematics, and it is known as a group, a symmetry group. And that table that I've invited you to multiply lots of matrices together is the symmetry group of the square. It's got a special name. It's called the dihedral group. Fabulous. So a little bit of an introduction to matrices. We started with McDonald's and we finished with group theory, which is not bad progress. Does anybody have any questions about the questions that I've gone through? Any comments? Has it been helpful? Ah, there's a thank you. Ah, there's a second thank you. Good. Cool. Okay, we'll finish there. Enjoy the rest of your evening, everybody. I hope that was a useful introduction to the sheet and also a useful idea, introduction to some ideas. By the way, did any of the Rubik's Cube solvers understand what I meant by this idea of conjugation? So what you very often do with the Rubik's Cube is you've got some trick that you know does something. And then what you can do is you can just manipulate the cube so that you've got the pieces that you want. Let's say you've got a trick that rotates 3 pieces. You just rotate the pieces that you want so they're in that position. You then do your trick so they rotate, and then you undo what you did at the beginning to take them back into the right position. Hard to explain without a cube, but if you've used a Rubik's Cube, you probably understand what I mean. Brilliant. Okay, thank you, everybody. Enjoy the rest of your evening, and I'll see you all again soon.